Hi everyone, thank you very much for joining us today on our webinar on the basics of lateral connection design. This is the first webinar of a series of 4, so we will have 3 more, one during each quarter. My name is Matt, I'm from the marketing team here, and then with my colleague Tobias in the engineering support group. So the format for today is very simple. We have a presentation that is about 25 minutes long, and we're going to have a Q&A session at the end. So I just want to draw your attention on how this works. So if you look on the right-hand side, you should see a panel, and there should be an orange button with a white arrow in it pointing towards the left-hand side. If you click on this, this will expand a new panel in which you will find a section called Questions. So I hope everybody can find this, because this is how we will be taking questions today. So if you expand this, so basically click on the orange arrow and then find the question section and just expand the question section. There should be a text field there where you can ask your questions. So just feel free to ask your questions throughout the presentation, but we will answer your questions at the very, very end. So just a quick reminder that we are recording this session today, so it will be available for replay. So on this, Tobias, are you ready?
Yes, I'm ready. Okay, thank you very much, Matt.
The floor is all yours.
Yeah, okay. Thank you very much for this introduction. My name is Tobias, and I will present today's webinar on the basics of lateral connection design. A little bit about myself. I studied timber engineering at the University of Applied Sciences in Rosenheim, Germany, and decided about 1.5 years ago to move to North America, and currently I'm working as a technical support engineer with Mightycon Timber Connectors. In today's presentation, I want to look at the historical background of lateral connection design and how modern base concepts are applied in our design standards in North America and Europe, and in the end compare those different design codes with each other. A lateral connection generally consists of 2 or more members that are designed to transfer a certain force component between each other. So the force has to go from one element in the other. In order to do that, we design with a dowel type fastener. In this case, it is a fully or partially threaded fastener in 90-degree installed here. Most design codes nowadays are based on the so-called European Yield Model, or EYM, which is based on the work of Knud Winstrup Johansen. Johansen was a Danish engineer and author, and introduced this European Yield Model firstly in 1949 in his book on Theory of Timber Connections. Johansen found 3 elementary effects when he did testing on different lateral connections. The first effect was the effect of the dowel itself, so he obtained a certain bending resistance of the fastener, so the fastener showed bending here. You can see that on the right-hand side in the picture down here, but also wood crushing effects that were influenced by the fastener diameter. Another effect of the wood itself, the wood showed a certain crushing resistance and also a dependency on the grain direction. The wood species also influenced this overall connection strength, as with a higher specific gravity, the lateral connection strength got higher. Also, one effect that Johansen noted was the axial effect of the bolt, but I'm gonna get to this a little bit later in this presentation. Johansen found relatively quickly that it is hard to quantify the connection strength of a lateral connection just by using one formula. So he decided to split up this connection in different failure modes. So one failure mode here only considers crushing effects in the side member. So we will see a linear crushing effect here in the side member. And the design standards in the US, for example, refer to this failure mode as failure mode 1S, whereas S stands for the side member. In the CSA UD6 or the EC5, this is relatively similar. So those also use the European Yield Model approach, and here the failure modes are called failure mode A. Reasons for this failure mode are relatively thin side members or large diameter fasteners, so relatively stocky fasteners or low slenderness, and therefore the wood is not able to deform the fastener plastically. Now if we turn around this connection, we can see the same effect can also happen in the main member, where we also see a linear crushing effect of the fastener in the wood. and this failure mode is referred to as failure mode 1M, whereas M stands for main member. Again, possible reasons, the same as for failure mode 1 before, is a thin side member, large diameter fastener, so the fastener is not able to be deformed by the lower embedment length. Combining those two failure modes now, we will see crushing effects in main and side member likewise. So we will here see around the shear plane and on top of the connection those embedment failures, but the fastener does again not yield, the fastener just turns within the shear plane. This is referred to as failure mode 2. Here the reasons are the same as for failure modes 1, as we still have a relatively thin side and main member, large diameter fastener, so a low slenderness. In order to make it a little bit more complicated now, we are looking at combined failure with fastener bending or yielding here along the shear plane and localized wood crushing effects. And this is referred to as failure mode 3S, whereas S again stands for side member. Here, now the reasons are that we find longer embedment lengths, small diameter fastener, so our slenderness goes up, and therefore the wood is able to deform the fastener plastically. In the next failure mode, of course, the same scenario can also happen. Here in the main member now, you will see the formation of the plastic hinge here in the main member with localized wood crushing effects. This is referred to as failure mode 3M. Possible reasons, here again, long embedment length, small diameter fastener, so the fastener is less stocky. The lever arm is enough to form a plastic hinge in the fastener. If we now combine those two failure modes, we will see formation of two plastic hinges inside the main member likewise, and localized wood crushing effects along the shear plane. And this is referred to as failure mode 4, or Eurocode refers to that as failure mode F, for example. And this failure mode here is considered to be the most economical or the most the best failure mode to be targeted, as both materials are exploited to the maximum amount possible. So the fastener is exploited by the bending strength and the wood itself is exploited through the crushing resistance. So here the reasons are relatively long embedment length, small diameter fasteners to achieve this very ductile failure mode. Looking now in the NDS, we get different equations that the designer has to calculate through. So each failure mode is assigned one equation, and this is relatively hard to calculate through. So I would suggest anybody who wants to calculate through those equations to set up an Excel spreadsheet or maybe use a ready calculated fastener capacities from design tables that are given by manufacturers, for example. And here, the minimum of those lateral strength values set will be governing the connection. There's a couple of influencing factors that go into those equations that are given by the fastener, which is the diameter. The diameter will influence the fastener crushing resistance and also reduction terms in the NDS for allowable stress design here, or also the bending yield strength of the fastener, FYB here. The bending yield strength only goes in formulas 3 through 4, because those are the only formulas where we actually look at the plastic deformation of the fastener. So here in those failure modes, we see this yielding happening of the fastener. The last influencing factor of the dowel bearing length of the fastener is the dowel bearing length. So for side member and main member likewise, and those go in formulas 1 through 3. And we don't see this dowel bearing length taken any action here in failure mode 4, because in failure mode 4, we already consider a ductile or plastic formation of a hinge here in both members before embedment failure throughout the entire side or main member. The wood itself also shows influencing factors. As I said before, the grain direction in the NDS, the grain direction shows an influence for fasteners larger than 1/4 inch in diameter. So we have to look at parallel and perpendicular to grain loading likewise. And lastly, the wood species shows an influence here. the higher the specific gravity of the wood, the higher the lateral connection strength. For example, balsa wood has a relatively low specific gravity. It will show a relatively low connection strength, whereas if we have the same connection in massive oak timber, we will see higher connection strength. Those failure modes can, on the next slide, be seen in this graph here in a dependency of the fastener capacity set here on the y-axis and the slenderness factor gamma here on the x-axis. In order to explain that slenderness a little bit, I want to look at the following example. For a 1/4 inch fastener embedded 1 3/4 inches in main and side member likewise, the slenderness gamma will be calculated to 7. Now looking at the graph on the left-hand side, we can see for a slenderness of 7, we reach a somehow plateaued out fastener capacity that does not seem to increase anymore. And the reason for that is that with the slenderness of 7, we already achieve failure mode 4 here, where we don't have influence of the embedment length anymore. So this failure mode is governed by the fastener bending yield strength. And North American design codes usually give minimum penetration lengths, which are between 4 and 6 times the diameter, and this is nothing else than the slenderness gamma. So mostly with if we go with those minimum penetration lengths, we will achieve failure mode 4. On this slide, it can be nicely seen how this failure mode 4 looks in real. This was a little dummy test that we did at UBC here in Vancouver, and you can nicely see the formation of the plastic hinge inside a main member likewise, and localized wood crushing effects along the shear plane. This is a very classical failure mode 4 here. Now back to Johansen's findings to the European yield model as it was firstly introduced in 1949. We can see those dowel effects of the fastener, so the bending resistance and the wood crushing effects are considered in the yield limit equations, and also the effects of the wood. So the wood shows a certain crushing resistance, which is on the other hand, again, dependent on grain direction and wood species. But what about the axial effect of the bolt? We did not see anything in the NDS yield limit equations here. In order to explain this axial effect of the bolt, I want to show the following example here. This is a lateral connection that is connected with a smooth dowel here. And once we start to displace this connection, we will see that a plastic hinge will form and the fastener will be pulled towards the shear plane once it starts to deform, because no end fixity is given here. So this is limiting the overall capacity or the ultimate capacity of the connection, and therefore this will fail at some point. But what if we now replace this smooth dowel with a fully threaded fastener, for example? If we do the same thing with a fully threaded fastener, we will see that once we start to deform the connection a little bit, that the threads actively prevent the fastener from being pulled towards the shear plane with the withdrawal action here. And through that, we will develop a normal force component here in the shear plane, which is directly translated into friction. And the higher load we put on this connection now, the higher this withdrawal capacity gets and more friction will appear in the shear plane. This is the so-called rope effect or string effect. In order to show this on a live video here, I want to look at this little video and explain that in the beginning here. You can see 2 fasteners installed in the side member of this H-block test here. So the heads are a little bit left out, the side member, and the thread of this fastener, so it's a partially threaded fastener, is completely embedded in the main member. So there's no axial resistance in the side member at all. Once this connection starts to deform, we will see that the fasteners will be pulled inside the side members, so as no end fixity is given here, and there will be a slight gap opening. But once the heads engage again, we will see the rope effect action here, and this gap will close and connection strength will go up again. So I'm gonna start this video now. I hope this works out for everyone. My voice will be cut out for a little bit. I want to check with my colleague Matt if that was displayed correctly.
We'll include a link to the video as well, so you can replay it in our follow-up email that we will be sending out either tomorrow or Friday.
Okay, perfect. Yeah, well, this rope effect, or string effect as it's called in the CS86, is unfortunately not included in the yield limit equations in accordance with the NDS. And CS86 included this rope effect in 2009 in the chapters wood screws and nails, but only resulting in relatively small capacity increases. And the problem is with proprietary fasteners like self-tapping wood screws, we mostly don't meet the diameter requirements of wood screws, chapter 1211 in the CSA, so we have to calculate in accordance with lag screw chapter, which does not account for this rope effect. So we cannot use it, unfortunately, for self-tapping wood screws in the CS86. The Eurocode, on the other hand, allows the addition of up to 25% of the axial fastener capacity, and this can in the end up to double the overall capacity of the screws. Looking at a little excerpt from the EC5 here, you can see here in the red circle, this is the axial characteristic resistance of the fastener that can be added to the yield equations of the Johansen part. In order to highlight the differences between the North American design standards and European design standards, I want to look at a small calculation example here. We look at a 1/2-inch fastener embedded in SPF loaded parallel to the grain. When we calculate in accordance with the NDS yield limit equations, we obtain a fastener capacity of about 390 pounds. Calculating the same with the provisions of the CS86, we will obtain a fastener capacity of about 580 pounds. So this is a nearly 50% increase. So there's already a difference to be seen here. But calculating now with the provisions of the EC5, respecting the rope effect, we will get a nearly seemingly astronomical value of 1,400 pounds. So this is a factor of 3.5 between the US and the European value. So why is that so? There's a couple of different influencing factors that go in the yield limit equations, and the densities are used as a mean oven dry specific gravity in US and Canada, which is a unitless measure of the density. And on the other hand, the EC5 uses a characteristic relative density at a 12% moisture content. So a mean density and a characteristic density is very different, and also the moisture content at 0% and 12%, we will see different volumes here in the wood. So this is different between Europe and North America. Another very important factor is the load duration, whereas the NDS is calibrated to a normal load duration with a CD of 1.0, which is approximated to 10 years. The CS86 uses a KD of 1.0 for standard term loading, which is defined as larger than 7 days. So 7 days and 10 years, this is quite a big difference. And this also explains why we can use such a high short-term loading factor in the US, which is 1.6 for our calculations. And the CS86 only allows a 15% increase for short-term loading. The EC5, on the other hand, applies a K-mode factor, which is calibrated to short-term and instantaneous loading at 1.0, which is defined for lesser than 7 days. So for example, wind loads. So this is very different, those load duration aspects here, and we cannot freely exchange those values. We really need to understand what each load duration factor means. A fastener specific property is the fastener bending strength, whereas in US and Canada, bending yield strength is used, which is a force over area value, so pounds per square inch in the NDS or Newton per square millimeter in the CS86. Europe applies a so-called characteristic yield moment, so a moment instead of a strength, and also again a characteristic value, so we cannot just interchange those fastener properties between the different standards. We really have to test those with the American standard test methods. And having a characteristic yield moment from a European technical approval does not mean we can guesstimate a bending yield strength of for the use in the yield limit equations in the NDS. We really need to test those values. There's a couple of approximations given in the NDS, but testing is always better than guessing. The diameter that is used in the equations, also in the NDS, we need to use the root diameter, same as in CSA86. Only in certain cases we are able to use the shank diameter of the fastener, and in the EC5 we are allowed to use the outer thread diameter with certain European technical approvals, which is very different. So we cannot just take this outer thread diameter and apply it to North American yield equations. And last but not least, the design approach is highly different between all the different design codes, whereas the NDS mostly applies the so-called allowable stress design. CSA86 and EC5 use a sort of limit state design, which however also differ from each other. So none of those values should be freely interchanged without knowing the exact background. So you can see that those are only 5 factors that go in here, and those conversions can really lead to serious hazards, and everybody that is new to fastener design should be careful with those conversions, because that can really lead to mistakes. And a very famous mistake of a conversion failure here was in 1999, when NASA lost the Mars orbiter because of such a imperial to metric conversion mistake. So mistakes happen, everybody knows that, but NASA only lost a ton of money. But if that happens in a building, the building can collapse, we can actually lose lives, and it's not only money. So this is really serious, and we have to really understand what we design. So in the NDS, therefore, we use ICC approvals that go along with the NDS for the calculation. Also for Canada, the CSA86 goes along with a CCMC approval. So all of those approvals fit the values that can be calculated with a design approach here. And also EC5 uses the so-called European technical approvals, and those should not be freely interchanged with each other, as that can really lead to conversion mistakes. And here at Mightycon, we try to give the designer values that you can really rely on. So we do a lot of testing here with local North American universities, also with North American lumber species, because we also have differences here. On this picture, you can see an inclined screw test that will be included with the ICC revisions, but we also do testing for shear, or here a lifting test for our lifting devices, so that we can really say our design values have the right amount of safety factors inherent, and we are confident with providing those tables. And these tables can be found in our literature. So here for the US and Canada, we have 2 different design guides where you can find lateral design values here calculated with the correct approach in the NDS or CSA86. And those design guides can be downloaded for free on our website. So everybody that is new to fastener design, I invite you to download those structural screw design guides. It's an interesting read and a good design tool if you want to use proprietary fasteners. And with that, I want to thank you very much for attending, and Matt will go through the questions here. Let's see if you have any interesting questions.
Thank you very much, Tobias. So we do have quite a bit of questions here, so we might not get the time to go through all of them. I see that our engineers have been trying to reply to them on the fly. So we'll pick a few, and what we're going to do is we'll include the ones we couldn't get answered today in the follow-up email to make sure that all these questions get an answer. So maybe one question here. In the presentation, you said that in some cases, a different diameter than the root diameter can be used. When would that be the case?
Okay, yes, the diameter, I'll just quickly put up that slide. I said that here, that the diameter in US and Canada has to be used as the root diameter, and only in certain cases we can actually use the shank diameter of the screw. I think I just gonna pull up that picture from earlier. can be seen here. Yeah, this is the formation of failure mode 4 here, and you can see that there are actually different diameters within this failure. So here you can see this is the minor diameter, so this is the smallest diameter that we find in the screw, or also we say minor thread diameter. And here we can see that the yielding of the fastener actually happens in this portion of the screw, but we also have yielding in the shank diameter here. So this is an interpretation. If we want to use the root diameter or the shank diameter here, of course, we always want to use the most conservative case, and the NDS gives us directions. If this root diameter is far enough from the shear plane, so yielding does not happen in the root section of the fastener, we can actually use the larger diameter. But looking at the test data that we gained over the last couple of years, we can see that even if we use the shank diameter here in our calculations, we still have enough safety factor on top of our fastener, so there's safety of about 4 to 5 on top of those yield limit equations. So definitely you can also use the shank diameter in the approach. So another question?
Okay. Yeah. How much does the mentioned rope effect actually influence the lateral connection strength?
The rope effect, yeah, I'm just gonna. So I think this question is addressed to the rope effect with a fully threaded fastener as we see it here. In generally, we see that the fastener is prevented from being pulled towards the shear plane here. And by being prevented, we have a lesser initial deformation. So the capacity or the connection is a little bit stiffer in the beginning. And we can also see in ultimate stages that the capacity, the ultimate capacity, will be about 50 to up to 150% higher than the capacity with just a smooth dowel. So the Eurocode equations are relatively close to estimating what the scenario in real will look like.
Okay, thank you very much, Tobias. So we're going slightly over time now. So what I would do is I would encourage people to keep asking questions. We'll leave the webinar open so you get a chance to ask your questions, and we will just make sure to get back to you after the webinar with an answer to your questions. And as I said, we'll try to pick the ones that are most common, and we will include them in our follow-up email. So before we let you go, we would like to let you know that we've been working pretty hard for almost a year now on a new CLT connection design guide. And basically what we're trying to do here is we're trying to create the most complete documentation for CLT connections in North America. That's the purpose of this guide. And what we've done is we've standardized the connections for CLT by using the ICC approvals we have for our products, but also using the NDS design procedures to make them as simple as possible. So we actually provide you with the design tables, and we try to make it as much as possible plug and play for you. So this design guide will be coming out April 23rd. So we will be sending out an email. If you're interested, you can let us know. It will come in a binder, so we're planning on adding on to it based on the feedback we get and questions. But this, the first draft, or I guess the first version of it, will be 80 pages long. So keep a look in your emails. You should be seeing this coming around April 23rd. And lastly, before we leave, just to let you know, we will be in Portland March 20th to 22nd. 3 of our members in the team will actually be there. So we always like this trade show because we bring our test frame. You can see it on the right-hand picture there, the green test frame. So we bring samples and we test connections. We test the limits of our connections. It usually makes a lot of noise. It's kind of fun. Engineers likes it. Engineers usually like it because you kind of get the real sense of it, like the real life connection, not just on paper. So if you're there, I would love to see you. It's nice to see you in a webinar, but it's much better to see you face to face in person. So if you're there, do stop by the booth. Would love to see you. So on that, just a very last reminder that the email will be sent out either tomorrow or Friday, and will include questions to your answers. the replay for the video, as well as some links to resources. I know some people ask about the resources, how you can get the resources, so we'll make sure we put the link in that email as well. So in the meantime, we'll leave the webinar open so you can keep asking your questions. If new questions pop up, just send us an email. You can see the email address here. It's info@mytcon.com. More than happy to send you an email, reply to your email with the answer to your question. So I want to thank you all for your time, and until next time, thank you.